Experiment LRC circuit.
When a vibrating mechanical system is set in motion, it vibrates at its natural frequency. However, a mechanical system can be forced to vibrate at a different frequency. The amplitude of vibration, and hence the energy transferred to the system, depends on the difference between the natural frequency and the frequency of forced vibration. The amplitude becomes very large when the difference between the natural and forced frequency becomes very small. This is known as resonance, and the natural frequency of the system is sometimes called the resonant frequency. At resonance, relatively little energy is required to get a large amplitude. One example of resonance is when a singer's amplified voice is used to shatter a glass. Electrical resonance is analogous to mechanical resonance. The energy transferred to a system is a maximum at resonance. The amplitude of the AC current, I, in a series LRC circuit is dependent on the amplitude of the applied voltage, V, and the impedance, Z. Equation 12.1. I is equal to V divided Z. Since the impedance depends on frequency, thus, the current will varies with frequency. The impedance is given by Equation 12.2. Z is equal square root of inductance reactance minus capacitive reactance. Square then plus resistance square. At resonance, inductive reactance, XL is equal to capacitive reactance, XC, and thus the impedance, Z is reduced to resistance, R. At resonance, the impedance is the lowest value possible and the current will be the largest value possible. The resonance frequency is therefore Equation 12.3. F is equal to 1 divided to 2 phi square root of inductance times capacitance. Measure the value of inductance, resistance and capacitance using an LCR meter and record the values as in Table 2.1. To use the LCR meter measuring inductance. 1. Disconnect the power supply. 2. Connect the red probe to plus slot and black probe to dash slot as shown in Figure 12.1. 3. Make sure the blue button is pops up. 4. Turn the knob to LX scale. 5. Read the result on the screen. Capacitance. 1. Disconnect the power supply. 2. Connect the red probe to plus slot and black probe to dash slot as shown Figure 12.2. 3. Make sure the blue button is pops down. 4. Turn the knob to F scale. 5. Read the result on the screen. Resistance. 1. Disconnect the power supply. 2. Connect the red probe to omega slot and black probe to COM slot as shown Figure 12.3. 3. Turn the knob to omega scale. 4. Read the result on the screen. Procedures. Part 1. Computer setup. 1. Turn on the interface and the computer. 2. Make sure the voltage sensor is connected to analog channel B. 3. Make sure banana plug patch cords is connected to the output ports on the interface. 4. Open the document P52 LRC Circuit.ds on desktop. 5. Set the signal generator to auto. Procedures. Part 2. Equipment setup. You do not need to calibrate the voltage sensors. The following setup shows the AC DC electronics board, EM 9656. 1. Connect a 5-inch lead wire between a component spring next to the top banana jack and the component spring at the right-hand edge of the inductor coil. Put the iron core inside the inductor coil. 2. Connect the 10 ohms resistor, brown, black, black, between the component spring at the left-hand edge of the inductor coil and the second component spring to the left of the top banana jack. 3. Connect the 100F capacitor between the component spring nearest to the one in which one end of the 10 ohms resistor is connected, and a component spring nearest to the bottom banana jack at the lower right corner of the AC/DC Electronics Lab's circuit board. 4. Put alligator clips on the banana plugs of the voltage sensor connected to analog channel B. Connect the alligator clips of the voltage sensor to the wires at both ends of the 10 ohms resistor. The voltage measured at analog channel B is related to the current through the resistor by equation 12.4. Current I is equal to voltage from resistor divided to resistor. 5. Connect banana plug patch cords from the banana jacks on the edge of the AC/DC Electronics Lab board to the output ports on the Science Workshop interface. The completed connection is shown in Figure 12.4. Part 3. Data recording. 1. Check the signal generator window. Set the waveform to sine. Set the output voltage to 3 volts. Set the output frequency to 10 Hz. 2. Start measuring data. Click Start in Data Studio. 3. The scope display shows the output voltage, V, from the interface, and the voltage, VR, across the resistor, channel B, as shown in Figure 12.5. 4. In the scope display, determine the voltage, VR, across the resistor, voltage from channel B. A hint: in Data Studio, click the Smart Tool button, XY graph, in the scope display toolbar. Move the cursor to a peak of the signal that shows the voltage across the resistor, VR, channel B. 5. Record the voltage, VR, in the table 12.2 in the lab report section next to 10 Hz. A hint: in Data Studio, the voltage is the second number in the Smart Tools ordered pair. 6. Adjust the function generator to 20 Hz. Repeat the process to find the new value of voltage and record it in the table 12.2 next to 20 Hz. 7. Increase the frequency in 10 Hz increments until 150 Hz. Repeat the process of using the Smart Cursor to find each new value for the resistor voltage, VR. Record each voltage value in table 12.2. 8. You can enter data into a table display and then show the data in a graph window by using the following steps. 1. Click Experiment menu. 2. Select New Empty Data Table. 3. The table has 2 columns labeled X and Y. The first cell under the X column is ready for you to enter a number. 4. Enter the first value of frequency, Hertz. Click TAB, and enter the first value of current equal VR divided to R. Click TAB to move to the second row. 4. Continue to enter values of frequency and current. Note: Data Studio anticipates the next value of frequency for you. 5. Select Add Display from the Experiment menu. 6. Click Graph, and then click OK in the Please Choose window. 7. From the summary list, click and drag Data, under Editable Data, to the new graph. 8. The graph shows that current peaks at about 80. 9. To add labels to the y-axis and x-axis, double-click on Editable Data in the summary list to open the Data Properties window. In order to get the accurate resonance frequency, another method is used to compare the phase difference from 2 signals from channel B and output voltage. In the display, temporarily remove voltage channel B. Click Voltage channel B to select the input and then click the Remove button in the Scope toolbar. Click and drag Voltage channel B from the summary list to the bottom edge of the Scope display. Drop Voltage channel B onto the Sweep Speed control panel. The Sweep Speed control panel will be surrounded by a dashed rectangle when the new input, which voltage channel B is on top of the control panel as in Figure 12.6. Click Start to begin monitoring the data again. You will observe an oval shape as in Figure 12.7. An oval trace means the signals are out of phase. Adjust the function generator frequency until the scope display shows a diagonal line, as in Figure 12.8. The diagonal line indicates no phase difference between input voltage, voltage channel A, and voltage across the resistor, voltage channel B. The frequency at which this situation occurs is the resonance frequency.